Welcome everyone to Design and Analysis of Algorithms. In this lecture, we're learning about my favorite problem, knapsack problem. In the last video, we talked about introduction and the problem definition. And this video, we'll talk about a variant called fractional knapsack problem. In the next few videos, we'll also learn about unbounded knapsack and 0-1 knapsack. So let's start. So let us start with the problem definition. We are given n items, A1, A2 up to An, and each item Ai has size Si and profit Pi. And we are assuming both the size and profits, they are integral. We are also given a knapsack which has integral capacity B. This problem, fractional knapsack, is also known as continuous knapsack. And our goal is to choose each item Ai up to some fraction Xi. So if we don't take the item, it's 0. If we take the item completely, it's 1, but we are allowed to take it fractionally. So xi can be a number which is fractional as well between 0 and 1, such that condition 1, the capacity constraint is satisfied. So if we look at a particular item, Ai, and we have taken xi amount of the item, then the contribution of that item in the capacity is xi times si, and the contribution to the profit is xi times pi. Our goal is to make sure the total capacity constraint, if we sum over all I in n, xi, si, that's the total size that we are having in the knapsack, and we are trying to maximize the profit, sum of xi, pi. So of course, you can see in this case, it's always beneficial to fill the knapsack up to its brim, so it's equal to B, we can do, because adding things will only increase profit. Now, as an example, in the last episode, we talked about the case when in Lord of the Rings, Sam is packing his bag for Frodo's journey. He is taking bread, he is taking cheese and other stuff. But these items may not be taken always integrally. You can break it. So instead of having a large bread, you can break it if you have less capacity. Or instead of taking the whole cheese, you can take only 1/10 of the cheese or make some cheese slices and take it. So in these cases, the items can be taken fractionally, they can be broken. And several examples we find for this problem in real life. Think of a emergency relief truck where there is some disaster and you are sending some supplies, maybe rice, dal, and spices, salt, and sugar, etc. So depending on the space, maybe you don't have, the truck has 100 kg capacity or 1000 kg capacity, and maybe you're left with only 30 kg. Then you don't need to put the 60 kg rice there. You can just take the bag of maybe 30 kg rice, you cut it and make it 30 kg and then put it. So we can fractionally take the items. Similar example is bandwidth allocation. There is a bandwidth and there are several service providers who are requesting for the bandwidth and they are saying, okay, I need SI amount of bandwidth and I provide PI. But even if you don't give me entire bandwidth, if you give me fractionally, I'll pay proportional to the size that I'm getting. That is exactly again a fractional knapsack problem. Now we start with some greedy algorithms, and for that let's take one example case where b equal to 10, the knapsack capacity, and there are 4 items. And each item has some size, profit, and profit density. For example, the first item, size is S1, profit is P1, and profit density is 11. You can pause the video, think about some greedy strategies, and then we can continue. Okay, I guess you have thought about some greedy strategies. Maybe you can think, okay, I will take the items, the maximum profit item, then second maximum profit item, and so on. So based on profit, sorted in the profit, maybe in increasing order or decreasing order, same with size, maybe in increasing order or decreasing order. But we'll see none of this work. For example, if you take whatever way you take by size or profit, you either get A3 or A4 because A3 and A4 has maximum size, maximum profit, minimum size, minimum profit in this case. But this is not the optimal solution. If you think, you'll see the optimal solution is this, where you've taken the entire first element and a part of the second element. And in this case, the items are packed according to profit density. Profit density is a ratio of profit is to density. And this is an algorithm developed by Danzig in 1957. So let's go over the algorithm. In the algorithm, we fill the knapsack greedily according to the non-increasing profit density. So in this example, highest profit density is 11. So we put 11 as much as we can. And the second highest is 10.5. Second item, we try to put, as we have only 4 units of space, we put this item and stop. So if you think a bit, you will realize in this algorithm, we'll pack at most one item fractionally. But why this is correct? To prove that the algorithm is correct, we'll follow the usual template for greedy algorithms that you have seen in case of minimum spanning tree, in case of unweighted interval scheduling. We will assume that the greedy algorithm is not optimal, and then we will create another solution from optimal, let's say opt prime, which is either more than the optimal solution or it is even closer to the algorithm solution than the optimal solution, and we'll arrive at a contradiction. That's the general template we have followed. So let's go over in detail. So for now, assume all items have distinct profit density. We don't need it because if the items have same density, we can just merge them together and consider a single item as well. But then if we assume that algorithm is giving some packing AI1, AI2, AIK according to non-increasing profit density, maybe last item can be packed fractionally. And this greedy solution based on profit PD greedy, profit density based greedy algorithm is not optimal. So we're assuming it's not optimal. Then assume some optimal solution, opt. And in opt, we consider the items according to sorted order. Maybe AJ1, AJ2, AJL. Now we are not assuming here that this AJ1 is packed completely. It can be packed fractionally. We have no assumptions here. Now the template as we used were first you find where optimal and algorithm differs. So you scan from left to right both the solutions, and remember both are sorted by profit density, and look at the first part where they are different. So these regions are exactly same. Not only here it is different. It could be the case of item AIX was packed here, and maybe some part of AIX was packed here and then AJY starts, or it could be the case that AIX starts here and AJY starts here. Both are possible. Now AIX is packed in ALG. This is algorithm solution, and AJY is packed in opt. Now what we do is exchange argument. We create another optimal solution which should be even better than the present optimal solution. So by exchange, by the property of profit density with greedy, we know profit density of AIX is more than profit density of AJY. That's the reason AIX was put, not AJY, in algorithm solution. Now what we do, we take a small amount epsilon from AIX and we put and remove the same small amount from AJY and put this here. So this off prime looks like this. Up to this point was still same, and then we put little bit of epsilon amount of AIX, and maybe earlier it was packed in optimal solution AJY XJY amount. Now instead of XJY we use only XJI minus epsilon amount for AJY. And this is called, we are calling opt prime. And what is the profit of opt prime? Opt prime has profit if profit opt minus, we have removed this AJY epsilon amount and we have added AIX epsilon amount. And we know that this quantity is larger than this quantity from the profit density greedy. This is more than profit of opt. And this is a contradiction. So algorithm always returns the optimal solution. I have not talked about linear program, but those of you know about linear program, you can think about this and how to write a linear program to solve fractional knapsack. It's an advanced question only for those of you who know about this thing. And the time complexity is quite simple here. We're just sorting the item based on profit density, and that will take n log n time in the sorting itself. There is an advanced question that you can use quick select. Again, I have not talked about quick select, but if you know about that, and then you can have a linear time implementation of the algorithm. Now we see fractional knapsack is so easy, you can solve in linear time. But instead of fraction, when you go to integral variance, where you cannot take item fractionally, you can either take item entirely or not, which is 0 or 1, or you can take multiple copies, but each copy should be integral, that is unbounded knapsack. The problem becomes much harder. It is actually NP hard. In the next part, we'll talk about unbounded knapsack, and then the parts thereafter, we'll talk about 0-1 knapsack. Thank you.